Hi everyone, my name is Rodrigo and this is my colleague Dio. And it is my pleasure to welcome you to this lecture about the Raymer Manned Mars Plane given by Dr. Raymer himself. Before we start, I would like to talk about the rules for this presentation. First of all, this lecture will be recorded. I hope no one has any problem with that. If you want to interact with our speaker, write in the meetings chat, or by the end of the presentation, you can virtually raise your hand and ask a question directly to him. I ask you to all to keep the microphones and cameras off during the whole presentation. Now let us welcome our speaker. Dr. Raymer is the president of the design and consulting company Conceptual Research Corporation and serves as program manager, configuration designer, and chief engineer for its various projects. Currently, these include the DARPA Flying Missile Rail, the Raymer Manned Mars Plane, and the proprietary high-altitude UAV, recipient of the prestigious IAEA Aircraft Design Award. Dr. Raymer is a recognized expert in the areas of aerospace, vehicle design, and configuration layout, computer-aided design methodologies, and design education. During his years at Rockwell, he conceived and did the layout design of Rockwell's entries in what became the F-22, B-2, and T-45 programs. He was also the head of air vehicle design for X-31, from Black Sheet of Paper to the configuration that flew. Dr. Raymer is the author of the best-selling textbook, Aircraft Design, A Conceptual Approach, and the well-regarded layman's book, Dan Raymer's Simplified Aircraft Design for Home Builders. Dr. Raymer, the floor is yours.
Yeah, hello, good morning, everybody. And sorry about the earlier troubles that we had trying to do this presentation. I actually was going through a computer meltdown and didn't know it. They wound up having to basically replace everything inside the computer to fix it. So hopefully we won't have that trouble again. And I can get through this talk. I've never had that happen in a presentation before. Anyway, my apologies. Okay, well, anyway, good morning out here in Los Angeles, and I guess good evening there in Europe. And I'm going to talk about a project that I've been working on for a couple of years. It's an unfunded project, so it's quite a labor of love. Although we're sort of looking for funding, it'd be wonderful to get some funding and be able to dive in deeper. But I've actually got a substantial amount of assistance from a volunteer team. You can see to the bottom right there. And those folks volunteered to help and did a lot of really neat work. And I'll be showing some of their work in this presentation. So let me just get right to it. Let's see, which button do I want to press? Well, not that one. I can't find which button is going to advance. There we go. Okay. Well, we'll start with some eye candy because that's always nice. And one of the volunteers is really good with CAD and also quite good with design. So he took the overall concept, did a lot of detailing, and came up with some wonderful CAD renderings, which I thought were sweet and nice. I like the fact that he has the little Mars helicopter sitting next to it, so you can get an idea of the relative scale. So that's basically what we're heading for, and trying to come up with an airplane that would actually fly people on Mars. So the whole project started with basically me just sitting in this office and thinking about some things. There's been a lot of work going on. People like Elon Musk are completely serious about trying to get to Mars. And so I thought, well, what happens after that? I'm an airplane guy more than a spacecraft guy, although I have done quite a bit of work in launch vehicle design. But when you get to Mars, I figure when we get a bunch of people there, eventually they're going to want some way to get around. We're pretty used to having airplanes here, and I figure they're going to want airplanes also. And so that was my basic starting point, trying to come up with some kind of a manned airplane. Pretty far future, of course. We're not on Mars yet, so we sure don't need any airplanes on Mars, at least not manned ones. But sometime in the future, maybe my lifetime, certainly your lifetime, there should be people living on Mars. And when there's a reasonable number of them, they'll need a way to get around. So I started out just thinking what the requirements would be for an airplane. Again, just making this all up, all by myself, sitting here in my office. And I remembered the famous Jeep, the original Jeep from World War II, which was developed for the U.S. Army. It was a government contract to develop a utility transportation. And it turned out to be one of the weapons that won the war, they say. It was just so useful. So I just wrote down what that does. And what that does is it carries two people, about 500 pounds total payload. And the Jeep can go pretty much anywhere. It doesn't go very fast, but it can go pretty much anywhere. And the Jeep had a range of 260 nautical miles. So I thought, well, okay, we'll just start with that and see where that gets us. We know that's a useful capability because it was the Jeep that helped win the Second World War. And I assumed from the very beginning that there are already permanent bases. There's people living there. I don't have to get them there. I don't have to get this flying machine there. Somehow this thing will be built on Mars. I'm not folding it up into a launch vehicle and launching it from Earth and any of that kind of stuff. So somehow it gets there, and I'm imagining some combination of 3D parts printed in place, and maybe some of the really difficult things might be sent from Earth, but they would be sent in disassembled form, not a flying form. So people on Mars would put the thing together. I also assumed lots of electrical power would be available. And this would be either solar or nuclear. And I'm guessing nuclear because there's not that much sun. There is some, but it's significantly less. So I'm guessing there's going to be nuclear power plants. So I assumed all the energy you need. And I'm guessing large pressurized buildings will be available by then. Now, we have inflatable designs that would be pretty easy. So there'll be a place to put this thing together. You're not putting it together out in a vacuum suit. You're in some kind of a big hangar. So with those as backgrounds, then I started working on the design and sort of start out with the end result. This is the vision of the thing. It's flying along, two people in there, great big huge wing, obviously. How do you take off and land? I assumed you have to have a vertical takeoff. Obviously, you're not going to have wheels and roll around the ground until you reach liftoff speed. So some kind of vertical takeoff. And I assumed that that would be rocket power. So we're using rocket power for takeoff and landing, and great big electric propellers for forward flight. So here it is landing, and then here it is taking off again. So that's kind of the basic end point. And how did I get there? So basic operational concept, a couple of things. First of all, it is manned, but I'm assuming that it has all sorts of wonderful computerized control system. Why not? Even today, those are easy to develop and you can hold the whole thing in your hand. So of course, we'll have something even better when we're on Mars in 2030 or 2050, whenever it is. So it'll be capable of flying on its own. In fact, I would assume that there isn't really a trained pilot for this thing. You sort of operate it the way you operate an elevator. You get in and sort of say, take me there. And maybe it's a little bit like a video game where you're flying along like an airplane video game. You're sort of pointing it and directing it and saying land here, but you're not doing all the stick and rudder stuff that a pilot normally does. In fact, as an unmanned system, it can fly to a programmed destination and carry just 500 pounds of cargo. So you load cargo in this thing and you push a button and say, go there, and it goes there, and then people there unload it and they push the button and it says, go home. Or you can be inside it. I'm assuming that the batteries are fully charged from a ground source. I have put solar cells in the weight statement so it can trickle charge them back up again. But basically, I'm relying on charged batteries for flight. And I had to think about how much capability I had to give it. You know, when you do a design, if you give it too much capability, it sounds wonderful, but you're not going to get there. It's not really going to work. So there's always a trade-off. So I was looking for sort of the minimum capability that would really be useful. And so the minimum would be 2 takeoff and landing cycles. In other words, you're here, it takes off, it flies there, lands, takes off again, flies back here, and that's it. So then you're out of ability. And it's a combination of battery power and then also, of course, the propellants needed for the rockets. So here's some of the design features. I came up with this using my RDS aircraft design software. Number of things you can see in this basic layout, starting with the passenger compartment. And we need that to be pressurized and we need it to be very lightweight. So I went with a geometry that we know can be pressurized and can be fairly lightweight, and that's a cap cylinder. Basically, this is a whole lot like an autoclave. It's a cap cylinder on both ends. And the front cap cylinder, the front cap is transparent. So I'm trying to minimize the weight of trying to put windows into a composite structure. Instead, there's a complete ring around there, a tension ring, and this transparent piece attaches to it. And we have pretty good technology for making lightweight transparencies, and I assume will be even better in 20 years. So that's what I'm assuming here. It does open like an autoclave. You saw the picture earlier. It unconnects and swings forward and out. A couple other things, I needed to get the wing high off the ground because of ground clearance. This thing is a huge wing. I need to get it far away from the ground so that you can land places and not have to worry about rocks somewhere along the wingspan or variations in the terrain causing trouble. So I got the wing as high as I credibly could by setting it up on a pod. Parapods, actually. I know it looks like it came out of Star Trek, but that's an accident. That didn't start that way. But the reason for this geometry with the V-shaped struts is for crash survivability. If this thing ever does hit really hard, I don't want the struts holding up the wing to push through the passenger compartment and rupture the pressure vessel. So I've got it set up so that if there is a hard landing, with a little bit of luck, maybe the wing and the struts break away, but they don't destroy the integrity of the pressure vessel. So that's what the reasoning was here. Let's see a couple other things. You see helicopter-like skids to land, and there would also be some skid-like sticks out near the wingtips to stop it from tipping sideways. No need for wheels, of course, because we're not going to do a rolling takeoff. That would pretty much be impossible on Mars. You'll notice 4 propellers. It's actually 2 pushers and 2 tractors. And the reason for that is I wanted pusher propellers near the passenger compartment to get the props away from the people, for safety mostly, and also for not having them in your line of sight for photography and such. But I wanted the outboard propellers to be forward strictly for center of gravity, trying to avoid having the design be too much of a tail-heavy design. In this original version, I had rudders, all moving vertical tails, but I didn't have any horizontal tails. And later when we did some airfoil design work, which you'll see in a minute, we found out that to get any good efficiency on Mars in this flight condition, you need a highly cambered trailing edge, and that's going to be quite unstable. If you put the center of gravity in the right place for the center of lift in that geometry, it's very unstable. So I had to add some horizontal tails. Okay, more features here. I guess we can talk about some of these later. One of the volunteers took that design out of my software and put it into CAD software that makes pretty pictures and nice renderings. So you can see here that the vertical takeoff rockets, which I'll talk about in just a minute, are located in those pods. They're slightly angled away from the center so that they don't kick debris back into the passenger pod. They are redundant, and the guy who did this didn't quite catch on to the redundancy because you need some cross ducting to make sure that if one side loses its stored propellant, you still can keep the other side's rocket engines running. So there is redundancy, cross redundancy. If one of these rockets fails, you basically shut off the opposing counterpart rocket, and now it's still balanced in pitch and roll, and you've got enough extra thrust that you can still land. If 2 of them fail, then you're having a bad day. But if one of them fails, it should be no problem. If 2 of them fails near each other, then you probably are going to be descending, and that's when this crash protection is necessary, as I was talking about earlier. Okay, I actually did a lot of the analysis in a spreadsheet that I put together using equations that are in the 6th edition of my textbook, trying to come up with the range based on my analysis, weights buildup and things like that. And it looks like we're going to get a lot more range than I was looking for, about 1,000 nautical miles total range. So that's 500 out and 500 back, which is really nice. Now, my suspicion is that by the time we actually get the real weights build up, we'll probably find that the vehicle weight is heavier than I think, which means there's less weight available for batteries, which means the range would be reduced. So it's nice to have quite a bit of a margin at this point. Let's see, I used, for these calculations, these were early calculations, I was using the classical aerodynamics that's in my software. And obviously CFD would be better, so we did some CFD a little bit later. So coming up to that. So here's the CFD, a guy named Felix Finger, who just got his doctorate and is now working, where's he working? In Germany, I forget where. He got a wonderful job with his new PhD. Anyway, he did this on a volunteer basis, did very nice work, came up with much better analysis of all the different coefficients. And it actually wasn't very far from the classical results. So that was good. We put that back into the performance analysis, and it still looks pretty good. We also needed to come up with an airfoil design. So one of the volunteers, I think it was Finger again, did some airfoil design, and I forget which program. I think it was Xfoil. I knew that before, but he did some parametric airfoil design, trying to come up with the very best airfoil for these very challenging conditions. Let's see, which airfoil was it? Yeah, okay. So this is the one that was finally selected. It still has a lot of camber at the trailing edge. And as I mentioned, with this much camber at the trailing edge, if you put the center of gravity in the right place for this geometry, the vehicle is very unstable. And that's not good because you wind up driving the actuators a lot. You wind up using up your battery energy, which is supposed to be there for propellers, and you're using that to move tail surfaces a whole lot. So there's a trade-off there. So in a further study, I would love to start looking at some airfoils that are a little compromised, but have less of a cusp at the trailing edge, and see what the true best optimal solution is. But again, this was a volunteer project, and we weren't funded to do all those optimizations. So as a first pass, this made a pretty nice airfoil, and that's what we went with. So that's what you see in the later geometry. We had another volunteer to do a bunch of structural design and analysis. And he is, let's see if I remember correctly, he is from Madrid, I think, or one of the universities in Spain. And went through and did a pretty complete internal structural design. And from that did the structural finite element analysis and came up with deflections. And you see at the bottom, the wing does deflect quite a bit. We can reduce the deflections by making it heavier. And so there's another one of those trade-offs, but this looks like an acceptable amount of deflection. Another volunteer did look at some of the stability aspects, and he decided to do a tail trade study. I wasn't running this as a tight project, telling everybody exactly what to do. Since they were all volunteers, I sort of said, you know, come on in and play around, do whatever looks like fun for you. So he decided it would be fun to do some tail trade studies. So he looked at different tail geometries and came up with basically longitudinal stability. And from that, we could pick the tail geometry and tail sizing. And then he also looked at directional stability and found that the original design was somewhat unstable directionally. And let's see, what was the fix? A slight, we had to increase the tail area to get it to the point. It doesn't have to be completely stable. If it's sort of neutrally stable in yaw, that's fine, because we'll have electric motors far out on the wing, so we can easily mechanize those to artificially stabilize it. And that doesn't cost any battery energy. We're not moving a control surface. We're just giving it a little more power on one side. Am I still there? Can you still hear me? Because it looks frozen here. Okay, there we are. I think I was frozen for a second.
We could still hear you, no worries.
Okay, great. Yeah, my face froze, so maybe it really did freeze. No. Okay, so anyway, with a little bit of increase in tail size, we got the level of stability, which is, as I said, pretty close to neutral. That was good enough. Okay, another volunteer did an analysis of the takeoff and climb, actually doing a dynamic simulation. And the basic profile is shown here. And we chatted a little bit, and I said, yeah, use this as a first approximation. Anyway, you know, this is really funny. The camera is zooming now. My face is huge. Are one of you doing that, or is my computer deciding that I need to have a giant balloon?
I think it's your computer.
Oh well, okay. All right. Maybe it's good. Okay. Anyway, just sort of sitting around talking about what would be reasonable. So when you start this takeoff, you go straight up some reasonable distance, something like 10 meters seem reasonable, straight up. By then, you're probably clear of any boulders and any other terrain features nearby. Maybe you've landed in a little bit of a valley or something like that. So 10 meters straight up, and then accelerating. And to accelerate, you use the propellers, of course, but that's probably not enough. It would take too long to accelerate. And the whole time you're accelerating, you're also burning rocket fuel to hold yourself up until you get going fast enough that the wing can hold you. So it actually made sense. And I added rocket engines for horizontal acceleration as well. We talked about maybe pivoting the rocket engines and decided that's just a little too much complexity, a little bit too much to go wrong. And those rocket engines, they weigh very little. So we just stuck a pair of those in the back. And that gave us what we need. So we're accelerating by the time we hit 200 feet of altitude. What is that, 80 meters or so? We're going fast enough that we can fly just on the wings. And this shows a trajectory result and showing accelerating up to about 60 meters a second, which is enough to hold yourself up with wings alone. We're actually cruising at a higher speed than that, but that takes us just over stall, so you can shut off the rockets. Okay, well, one of the other volunteers decided to play around with the cockpit. And I had basically laid out the geometry based on myself sitting here in my office with a tape measure and also comparing it to sort of a standard man. I've got a standard man in my CAD system. It's a 95th percentile standard man, so it's a pretty big guy, a little bigger than me. So I laid out the cockpit, and this volunteer looked at possibly making the cabin smaller by some staggered seating, which is a good idea. Even if you don't make the cabin smaller, staggered seating does definitely give you more internal room. So looked at that, also looked at actually sizing the structure of the cabin based on applied loads, including pressure. And let's see, I forget what all is here. There's here's a buildup showing a possible internal geometry. So there's some side rails there, and then the seats fit in. And notice the seats are staggered. There's a heads-up display in the front. Looks pretty good to me. This could be controlled by some kind of a little control panel in front of you, or you could actually have a little handheld controller. I mean, it's going to fly like a video game. Why not control it like a video game? In fact, you could even use the actual video game controller that's popular in that time period, which probably isn't the one we use today, but you know, it's probably not too far from it because the ones today are pretty good. That's how I would do it. You know, that way there's very little training time. You know, anybody that grew up in that generation will say, "Get out of the way, I got this." No. Okay, and another one of the volunteers also took a look at the cabin and all that, and I let him. It's volunteer, so let him have fun. And this guy, very creative and slightly different take on it, but you know, it's all good. So here's a different way of doing it with an interior that's sort of a solid one. It actually isn't quite my vision because I wanted all the internal things to fold out of the way for cargo. This is nice, and maybe there's going to be a manned-only version of it, and then this interior would make a lot of sense. So, but much better artist than I am, though. I can't draw that good. Okay, and then some actual calculations. And it turns out there's closed form equations for all this stuff. Any mechanical engineering handbook has equations. You don't need finite element analysis for this. You know, that's like using FEM on a stick. You know, we've got equations for that. So he was able to come up with internal weights, and those weights were compatible with the weights I had used in my initial analysis. So my guesses weren't too far off. And I did that just on a pounds per square foot basis. Here's additional internal design by another volunteer, Aviv Levy, a fellow down in Israel. Very good conceptual designer in terms of all this kind of stuff, interior layout and things like that. Anyway, I like his arrangement there, and he's got a seat that is very lightweight and folds out of the way. Remember, you're only sitting in a 1/3 gravity. So you don't need a big, comfortable chair like you would use to, you know, sit and watch the football game here on Earth. You hardly need anything, just little plastic supports to stop you from moving around. That's kind of what he's showing here. They're very lightweight seats. So that's pretty clever. Let's see, a little more look at laying out this concept and some of the internal arrangements. And I think this one looks really cool. I like the other one too, though, actually. I like them both. Anyway, I'll kind of skip through some of these. Okay, well, with that initial work by myself and the team, time to do a -2. And if you've read my book, you know that you never build that first drawing, the -1, you never build that. So here's the -2, and it's not done either. And we'll probably be up to the -20 before we decide, okay, this is the one we'd like to build. But this is definitely getting closer. And shows some more of the features, and the main difference is adding the horizontal tails. But there's some more subtle differences as well. There's things I'd like to do now to change it. And if I can get some follow-on funding, great, we'll do it. So let's see, here's some more of the images from Aviv. And this is the -2, so it's a little bit different. All right, so that's some of the stuff that we've done. And where are we with this? Well, right now it's kind of quiet. I'm actually insanely busy on some other things. I've got a DARPA contract that's coming to a hardware demonstration real quick, and that has much of my attention. And then I have 2 other contracts that I'm supporting, so kind of difficult to do all those things. So right now I'm really not doing much on it. I hope to get back to it starting in January and maybe take it a little further and try to get some funding. But what we've done so far, I think, stands up. I think this works. I think there is a viable manned airplane that would fly on Mars. And I think this is probably the right approach. Other people can look at others, and someday maybe we can do a great big system engineering trade study. But at least based on my experience and my first look at this, I think something like this is probably the right approach. Rocket thrust for takeoff and landing, big propellers, electric powered, and a big wing. Oh, I didn't mention, I guess I didn't bring the slide along, but I didn't talk about the rockets themselves. A fellow named Jim French, who I've known for years and is the co-author of one of the AIAA launch vehicle spacecraft books, a very experienced guy, JPL, involved in most of the space exploration missions from the 60s, 70s, and 80s. Anyway, he has been looking for quite a while at a rocket like this. And the thing that makes it neat is that the propellant is cracked out of the Martian atmosphere. You can actually apply electricity, which I assume we're getting from nuclear power plants. And from that electricity, you can crack out oxygen and carbon monoxide. And that can be liquefied and stored. And it's been demonstrated doing that from an atmosphere like the Martian atmosphere. So Jim French gave me rocket motors to use based on his analysis of the specific fuel consumption, or as rocket guys say, the ISP of that propellant. So that all seems to work. In fact, Jim thinks that I'm being too conservative. He thinks that I should put the actual plumbing on the vehicle so that it can make its own propellant. He says that the hardware to make the propellants would weigh less than carrying the propellants on my mission. And so you'd fly out with nothing, when you land, there's nothing in the tanks, and then you wait a while and the tanks slowly fill themselves up. That kind of scares me. I don't want to be stuck 500 miles away from base on Mars, waiting for a tow truck to come take me home because my propellant cracking mechanism didn't work. So I told Jim, yeah, we'll put that on the second version. We'll put that on the B model. So he kind of laughed and said, okay. But as far as putting that on a permanent manned base, it's a no-brainer. It's very easy. So we can have that sitting there filling up these propellant tanks, and we can fill it with enough propellant, as I said, for an out and back mission. So that's my baseline. Okay, let's see. What else have we done? This plane is designed for exploration, research, cargo transport, photography, and maybe even a little bit of fun. Sure looks like fun to me. And of course, if there's multiple manned settlements, then how do you get from one to another? It looks like it works to get a payload of 500 pounds. That's 500 or the people plus whatever's left over. So it's not both, but it's optionally manned. So when you need 500 pounds delivered, it flies itself. It looks like 260 miles range is very doable. In fact, I'm getting a whole lot more, but I'm pretty sure some of that will disappear by the time this thing flies. The VTOL part seems to work. With rocket thrust, you might kick up a whole lot of dust and sand and debris. We've seen that with the Mars landings, but it's not that bad. And I've angled the rockets away a little bit, so I don't think it's gonna come into the vehicle. Let's see, what else have we got? Yep, well, nobody needs it today. This is for the far distance future, so I'm doing it sort of for the fun of it, but it's an interesting project. So let's see, I think that's my last slide. Yeah, okay, there's more information on my website if you want. There's some view graphs and such that you can download, some reports that we've written. They're not super duper professional quality because it was all done for free, but I think you could follow what we're up to and what we're doing. So is that the last? Yeah, so here's some more renderings of this thing coming into land. These are better than the ones that I did. And I think it looks really cool. Yeah, here comes Bob coming back from his exploration. And when it lands, then you hop out. Okay, I'm done, right at 30 minutes, and open to questions. I've got plenty of time, so very happy to answer questions. How about first questions on the manned Mars airplanes? And if there's any general questions later, you could throw those my way too.
Thank you very much. I'll let you talk now.
Okay, so we have a question from Andrea. You could speak if you want.
Okay, thank you. My question is something from the Ingenuity experience that we have learned that can be applied here, since we are talking about aircraft Mars?
Well, funny you should say that, because right after doing this for free, literally just for the fun of it, I've actually gotten involved in a project for an airplane that flies at extreme altitude on Earth. And the conditions flying at extreme altitude on Earth are very similar to flying on Mars in terms of lift coefficients required, Reynolds number, and some things like that. So there's definitely a lot of synergy back and forth between this project and a lot of the high altitude airplanes. People are doing what they call high altitude pseudo satellites to sort of fly around and maybe take pictures and stuff like that. So yeah, there's a lot of synergy back and forth. Some of the things, of course, don't carry over. This rocket-powered vertical takeoff isn't necessary here, because if you design an airplane to fly at 80 or 100,000 feet, when you get down to sea level for takeoff and landing, it's flying at a very low speed. It's no problem landing it. Hang on a second, I'm getting a call and I'm sure it's junk. So yeah, there's a lot of synergy. The propellers, the electric motors, solar cells, all that stuff, there's a whole lot of synergy to what we do on Earth.
Sorry if I reply. My question was about the Mars helicopter Ingenuity.
Oh, what was the question? I didn't hear anything about the helicopter.
So my question was if there is something that we have learned with the Mars helicopter Ingenuity that can be applied to this project as well.
Oh, if that was a question. I didn't hear the word helicopter at all before. Sorry about that. Yeah, well, let's see. Well, there's a lot of connection between those in terms of flight on Mars, the atmospheric conditions, the Reynolds number, and all that sort of thing. Helicopters are very different from airplanes as far as design, but some of the underlying technologies are the same, of course, lift, airfoil shaping, stuff like that. When you talk about what we learned from flying the helicopter on Mars, well, we usually learn everything long before the vehicle flies. The only thing we learn from the flight is if it doesn't fly and we go back and find out we made some huge mistake, then we learn something. But almost always on a project like that, you learn everything developing the design. That's why we airplane designers, we're actually not all that excited when it flies, because we knew it would. I mean, it's neat to see, and wow, look at the pictures, but we knew it would. And if it didn't, then we all get excited. Ooh, it didn't fly. Why not? Why not? Let's find out why. Anyway, yeah, there's a lot of connection in the technologies. And there are people, by the way, who say that the manned airplane should be a helicopter, and that's fine. I didn't study that option, and I'm not prepared to comment on it, but certainly you could take a fuselage like the one that you see here on the screen and scale up Ingenuity to fit on top of it with great big propellers and see what you get. With the helicopter, though, there is always the issue of the advancing blade in forward flight, and that can very quickly limit the forward flight speed of a helicopter. That's always the problem with helicopters. That's why they fly slow. You can read about that in my textbook if you're not familiar with that problem, but it's a huge problem. And if you're flying on Mars, where the Mach number is even lower than on Earth, you really have to watch out for that. Okay, more?
I just want to thank Andrea for his question. And my question is, when we want to do when we do concept designs, we all learn about what we did and the mistakes we did. What would you have done differently if you had to start now this project?
Oh, well, that's the normal evolution. You start out with your best guess, and then you do a -2 and then a -3, et cetera. You change the design. And also sometimes you do a complete alternate design. That's a very good thing to do in any design study. When you think you've got the best configuration, then force yourself to do a different one, just to see if you might find something better. And if you can't force yourself to do a different one, then get somebody else to do it and say, do anything but this. And we'll see how it looks. If I were to do it differently, what would I look at first? Well, I don't know. I might try to get away from this thing of having the wing up on the big pylons. That's a little bit odd looking, but I mean, I've still got the reasons I did it, but maybe I could come up with a different solution. Have the fuselage directly attached, and maybe I just have very long landing gear or something. That might be of interest. Certainly the number of electric motors is something that could be very different. There's designs flying with dozens of little electric motors. That might be a better approach. It would certainly be worth looking at. The overall wing geometry, I went with a simple wing with a non-tapered planform all the way out to the tip. And taper has benefits. It has problems too, but if it's not too difficult to build it, say let's imagine all the ribs are being 3D printed, then who cares that they're different shapes? Then maybe a tapered wing might be better. I put a little bit of a dihedral and a swept section all the way out at the tip. I haven't been able to analyze that to see if that turned out to be a good thing. The reason I did that was to try to get a little bit more roll authority, because I didn't want to put ailerons on the design. So maybe that's good, maybe it's not good. I could quite possibly use a twist, use aeroelastic effects, and get all the roll control I need out of twisting the wing, using the elevators to twist it. It's a little counterintuitive, but I could deflect the elevators the wrong way, twist the wing, and get the roll control I need. Anyway, those are some of the things I'd probably look at. If I had more time, I could keep on going. That's what I do for a living. My main personal skill set is throwing out lots of crazy ideas. It drives my wife nuts, because when we're talking about something that we want to do, I'll throw out an idea and say, well, why don't we do this? And she'll go, okay. And then a minute later, I'll go, well, we could do this other thing instead. And she'll go, well, which one do you like? I don't know. And then I say, well, here's a third one we could do. And after a while, she says, just tell me the one you want to do. Don't tell me all the others. Anyway, but when you're an aircraft designer, it's good to be able to come up with all kinds of other ideas. Looking at it, my transparent nose, it sure looks cool, and I'd love to fly behind it. Maybe that's heavy. Maybe some other geometry would be lighter in weight. Stuff like that. Okay, next question.
Thank you very much. We now have a question from Danielle Pint. Go ahead. You can turn your mic on.
Hi. Actually, I have a couple of questions to put. One of them is asking why would the team stick with a long wing, such a large wing design, and not something like a tandem wing or maybe like a biplane or something?
Tandem wing really wouldn't help here, because you don't naturally have a fuselage long enough to get the two wing segments away from each other. So you'd have to add some kind of a stick to it, which is extra structure and drag. So I don't really see a tandem wing having any role, at least in this geometry. The wing has to be huge relative to the required fuselage. I mean, all you need to carry my design payload is that little cap cylinder. So I wouldn't want to have to lengthen the fuselage just to provide a place for a tandem wing. Now, putting a biplane wing on it is a little more interesting, and that might be a very interesting trade study of a second wing, which basically lets you get a lot more area for the given span. But biplanes have their own problems. They're good with structural weight. They're very good with structural weight, but they're not so good aerodynamically. There's a lot of interference. And to get it to work, you need to have the two panels pretty far apart. And the classical guidance, the separation required is based on wingspan. So if that classical guidance holds up, then the upper wing has to be way above the lower wing. And so it would be an interesting trade study, perfect thing for CFD, to see if that really holds up for a very high aspect ratio planform. Of course, the high aspect ratio is to give you low drag in forward flight. And maybe that's not necessary. Maybe we can have a little bit more electrical power and a little bit lower lift to drag ratio, and maybe we get an optimal solution that way. So your question about the biplane is, it's actually interesting and could lead to lots of interesting optimization. Are you volunteering?
I mean, I do like the idea of the project.
That'd be a great trade study. Yeah.
I ask this because such a large wingspan seems like it would have a lot of weight in keeping it all together, especially in flight. With all of the changes in pressure and everything, the wing would be shaking a lot, and it being so large, a lot of weight would be spent on just keeping it together. And that's why I asked,
Yeah, that's a completely valid point. And it is relatively heavy because of that span. So if we could get away with either cutting the span down with a much lower aspect ratio, or something like you said, putting a second wing on top, that would save a lot of weight.
And I actually have, it's not large study, but I know a few of the trade-offs that biplanes give, and generally the bad things that they do have, it's at height speed, and I don't think that this plane would have to fly at a high speed, so maybe it would be actually a good design, maybe.
It would be worth looking at. Yeah, the drag of the bracing of a biplane is a problem, and this is not a low-speed aircraft. It's flying, I should remember this, I think it's at about 160 or 180 knots, and that's so that the wing doesn't have to be even larger. So even though this looks like it would float like a feather, it actually has to get going pretty fast before it can carry itself just on the wing. So that's, something to consider. On the other hand, what really matters is dynamic pressure, and it's a very low dynamic pressure. So it might be a good solution. It would be a great trade study. I would be very happy to see a trade study of the possibility of a biplane, and also just simply a much lower aspect ratio wing.
I actually have another question, which is a plane like this would, some parts would be able to be built on Mars with some kind of equipment that would be put there. But at least in my mind, I think that some components wouldn't be able to be built on Mars, and they would have to be sent from Earth. And what kind of components would those be, if they even exist, and how detrimental to the development of the airplane would those cases be?
Yeah, that's a good question. And we haven't done any kind of a detailed study. You can probably imagine yourself what those would be. Things that are extremely high strength parts. You probably wouldn't make those by 3D printing, at least not today's technology, but 3D printing keeps getting so much better that maybe they'll have 3D printers that can make these very highly loaded fittings, wing attachment fittings and stuff like that. Things that are very large might be trouble, because I doubt they're going to make a 3D printer that can make a 40-meter long wing, or however big this thing winds up. So it may be actually that you would want to send the spars, maybe, although certainly you'd rather not, but who knows, maybe you need to. They don't weigh much, they're just big. Things like electric motors and such, and avionics, it'd probably be a while before they make those themselves on Mars. So you'd probably send that kind of stuff. Some of the subsystems, or most of it, you'd probably send. So yeah, you'd have to send some of this stuff up, but of course it doesn't weigh much, so you can just carry it along on some mission to carry people and supplies. Yeah, that'd be a real detailed study. But another thing also is that we make composites now with graphite and epoxy. And of course, those are based on petrochemicals. And that's one thing there doesn't seem to be on Mars is any oil wells. So unless we can make this stuff out of Martian sand, that might be an issue. It may be necessary to send feedstocks up so that you can make stuff like that on Mars.
Yeah, thank you so much.
You're welcome. Good questions. More?
So I don't think we have any more questions. We can wait a little bit to see if anyone wants to ask something else.
I like this CAD picture. I think it's really cool. I told him to do something different. At first he had just a regular flag, and I said, why don't you make a 4-part flag with the different, the 3 organizations that would probably fund this, and then the 4th flag, make up a flag for our company, whatever it is going to be, you know, the Mars Airplane Company. So he did that, and then I saw later somebody else did the same thing with this single flag with 4 different elements to it. Another thing I told them is to don't assume normal spacesuits. That's just too John Glenn technology. Let's assume something different. And people have been looking for years at pressure suits that use mechanical pressure. So it's like a tight wetsuit, only it actually squeezes you to apply the pressure that you don't get from the atmosphere. And so that's why it looks like they're pretty casually dressed for being in a near vacuum. But you still need a helmet. I don't think any of us wants to have something squeezing our head. So you need a helmet with air in it. But I told him for the rest, make it tight like some kind of elastic clothes. It's just a notion, just a concept.
Yeah. Just
the other thing, they still need a backpack for the life support stuff. So I think they left their backpacks behind. Okay.
I actually have a question. So far, what was the biggest difficulty you have encountered in this project?
Biggest difficulty? Oh, it's a very different, very strange airplane, but it's an airplane, and the usual things that apply during aircraft design apply. One of the difficulties was making sure I wasn't screwing up when I adjusted all the calculations for the Mars gravity and Mars atmosphere. And it's pretty easy to do it wrong. Our equations are all based on Earth. So whenever you have something that is an acceleration, you have to accelerate the full mass, not a third of the mass. Whereas when you're talking about like a static force or something, or the thrust of the rocket, then it's the adjustment for gravity. To hold the vehicle up with rocket thrust, it's something like a third of the thrust required on Earth. But to accelerate it upwards, to get your usual helicopter 0.05 g acceleration, you need more thrust because you still have the same mass. So just dumb things like that took a lot of effort. And who knows, I probably still screwed some of them up. Have to go back and check again. Yeah, that was probably the main thing different from a normal airplane. And of course, getting a good weight estimate is always difficult. And for an unusual design like this, operating in an unusual environment, there was a lot of guessing involved. I used statistics from airplanes here, and of course, they don't look anything like this. So there was all kind of adjustments and corrections. So I was pretty glad when that cabin calculation and also the wing calculation, when they came out fairly near what I had estimated, a little bit higher, but I had put in some margin. So I was happy with that. But if we do this in exhaustive detail with a big team, I wouldn't be surprised at all to find bigger discrepancies. That's just how it works. So that's probably a big thing, the weight estimates.
So you think the design of the airplane is going to be similar in the final dash?
Well, I don't know. We'll see where it takes us. I'd like to keep evolving this one for a while, but I'd also like to do some alternate designs. There's certainly other ways of doing this. I think as a first try, this is as close as I can think to the right answer. but I've been doing aircraft design for too long to think that my right answer is for sure the right answer in the end, because you just never know. You learn things. You might learn that this one just flat doesn't work for some reason, or you might come up with another configuration, and as you look at it, you start to say, hey, this has a lot of benefits, and this configuration doesn't give me that problem that's causing trouble with the first configuration. And as an aircraft designer, you just have to be willing to make the change. You can't fall in love with your own design. I mean, I think it's really cool. I like it. I think it's really cool. But if something better came along, just watch how fast I switch, because I'll go with the best design. Now, I like it more if the best design was my design. That's my preference. But even if someone else did the best design, I'll go, okay, yours is better. All right.
I don't think there are any more questions. I'd like to thank you all for being with us today. Dr. Raymer, I want to thank you personally, so I want you to say just a little longer to thank you in the end. And everyone else, I hope to see you in any other opportunity. Thank you for being with us today.
You're very welcome. Thanks all for attending. Good questions too.